Well, thank you all for having me here today. This is an incredible part of the state and of the Southwest, so I was really excited to make my way down here and talk to you all today. One thing I will caveat is I will also be talking about data limitations and data gaps as well. So I can't promise to satisfy all of your information curiosities, but what we're gonna do is spend more of our time going over an overview of groundwater, of this basin, and start to think about next steps that communities can take to really get plugged in to your regional groundwater resilience. So a quick overview of today's talk. Like I said, we're gonna go over some groundwater basics. I give talks all over the state, and it's really helpful for me to understand my audience and who I'm talking to. We'll get into some specifics of the San Simon Valley subbasin, where we are right now. And then, as I mentioned, getting into some groundwater resilience opportunities for communities. So just stay along for the ride, and I'm hoping to have some time for questions afterwards, and if not, you can find me during lunch. So a quick game I like to play, groundwater myth or fact. The first one, so what we're gonna do, this is interactive. So if you think it's true and it's a fact, thumbs up. If you don't think it's true, thumbs down. If you're not sure, maybe like thumbs in the middle, and try to like raise your thumbs a little high so I can see them. So the first one, groundwater is a big lake underground. All right, I'm seeing a lot of thumbs down. This is normally the first misconception that I get that is helpful to just clear from the very beginning. Second one, groundwater comes from rain and snow. Thumbs up, all right. Groundwater is influenced by soil and geology underground. All right, this is a pretty knowledgeable audience. It's really helpful to know who I'm talking to. Groundwater ages can range from days to millennia. We got thumbs up, some thumbs in the middle, all right. And human activities can influence groundwater. All right. I'm glad we cleared that one up. And so this schematic from the Water Resources Research Center, I really like to give a broader overview about the interconnections with groundwater, with things we might do as humans, including irrigated agriculture and recharge basins, thinking about how things tie in to our landscapes, especially in our mountainous areas, our valleys, our riparian areas. But really my favorite thing about this figure is that it shows groundwater as occurring within sediment or within rock. Very often people think that groundwater is this big lake underground, and I have to really encourage people to think about it more like a flooded sandbox. That you have all of these pore spaces that are filled up with water, and that is probably my favorite part about this figure. Another thing that's really helpful to just kind of clear up from the very beginning with my audiences is that groundwater can really range in age from just a few days to thousands of years old, tens of thousands of years old. And in our part of the United States, our groundwater can be really old. And in some areas, this is not easily replenished. This can also vary within a single area. This figure down here on the bottom right shows that when you have more shallow aquifers or groundwater, that can have a really high connectivity to the ground surface and be just a few days or a few years old. When you get into groundwater that might be deeper underground, especially those below what we call confining beds, or the beds that kind of keep groundwater pushed down, that groundwater can be a lot older and respond on different timescales, even in the same area. One thing that this figure does not include is that you can also have faults and fractures in the ground surface that can really get groundwater deeper underground much more quickly, which is important for us to know, especially when we're in areas that have mountains that can really have a lot of those faults and fractures in them. But one of the things that is really helpful in kind of communicating or talking about groundwater is getting on some common terminology. And one of the things that we like to do as hydrologists is talk about groundwater as a savings account, as some kind of store of value that we want to think about what we're putting into it and also what we're pulling out of it. So to kind of take this a step further, because you might hear some of these terms as I'm talking, when we're groundwater budgeting, we're thinking about our inflows, what we're putting in, our deposits, our paychecks, and also our outflows or our withdrawals. The changes in storage is basically like looking at our changes in our account balance and thinking about what is that balance of inflows coming in versus our outflows. How much are we spending versus how much are our paychecks? And then I want to also note that these things can change over time. They can change seasonally, it can change year to year. We just heard about all of these different types of changes that can happen in the climate and with our rainfall, and all of that has implications for our groundwater as well. But similar to looking at our climate, we can also look at long-term trends to see how things are going. Some examples of our inflows into groundwater are, of course, rainfall, stream flow, especially streams that might be losing streams where that water is coming down underground, groundwater recharge areas, and then also groundwater flow from adjacent basins. Some of our outflows can look like surface runoff, especially when you have streams that are supported by groundwater in the form of base flow. Losses to the atmosphere. I want to thank our previous speaker for getting everyone familiar with the term evapotranspiration, or ET, so I didn't have to do that. Groundwater pumping, as we know, can be a major outflow from groundwater, and then also groundwater flow out of the basin as well. And here in the San Simon Valley groundwater subbasin, you have some combination of all of the above happening. So this area, as most of you know, we are down here in the southeast part of Arizona, southwest part of New Mexico. This was a very interesting groundwater subbasin because it also extends into New Mexico. One of the interesting things I found as I was digging through all kinds of reports to put together this presentation was that that little sliver that extends into New Mexico is not always considered in some of our statewide reports that kind of cut off that boundary at Arizona. This basin is situated across 3 different counties: Cochise County, Graham County, and then also Hidalgo County in New Mexico. I think this is the only groundwater subbasin in the state of Arizona that is like this. We get 10 to 28 inches of rain per year in this basin. That really depends on where you are in the mountains versus the valley bottoms. It's bounded to the north by the Gila Valley subbasin, so groundwater does flow out of this basin and into another subbasin. It's bounded by the east by the Peloncillo Mountains, and apologies if I mispronounce any of these. I'm coming from Tucson. It's bounded from the south by the San Bernardino Valley groundwater basin, and that actually brings groundwater into this subbasin. And then on the west, you have a combination of the Pinaleño Mountains, the Dos Cabezas, and the Chiricahuas. What's also very interesting about this basin, I don't know if this has a pointer. It does? This? Oh, there we go. Okay, so one of the interesting things about this, and I'm having a hard time finding it. Oh, there we go. So in the headwaters of the San Simon River, there's a cienega that is an old groundwater supported area in the form of base flow. So that is also an area where you had groundwater surfacing in the past. So the history of this subbasin is really intricately tied with the history of agriculture and agricultural pumping. Something that I found very interesting in doing my research for this area, and this all comes out of a technical report from the Arizona Department of Water Resources as they were constructing a groundwater flow model of this area, is that the history of agriculture began over 100 years ago. Many reports said in 1910 when artesian or those flowing well conditions were discovered in this area. There was this period of pumping that initially started in the early to mid 1910s that really declined after World War I and didn't pick up until after World War II. This is pretty consistent with what we see in a lot of the basin and range province aquifers throughout southern Arizona. So throughout the 1950s to the early 1980s, that's when we saw a major increase in pumping in this region that seemed to drop off right at the beginning of the 1980s and has stayed more or less constant, bouncing up and down here and there since that time. Overall, there is not a lot of information that's used for, or that's available for kind of early agricultural coverage, pumping, and practices. There's some old reports that document about 1,900 of acres in 1915, but there really wasn't documented agriculture until the 1970s, and there wasn't a lot of really good high-resolution data coming out of here until about the mid-1990s. All of this to say that, this isn't an exact graph that you should count every number. These are estimates that were really developed, a lot of them based on old power records to kind of back into how much pumping has occurred over time. And this drop-off in the early 1980s, we're gonna come back to that in a little bit. So just keep that date in mind. So one thing that I'm not sure many people are familiar with, again, this information kind of varies across the state, but just a quick show of hands, how many of you are comfortable with terms like depth to bedrock? How many of you have heard that term? Okay, about half. So one of the things, this helps me understand like how deep to get into things and also how to make sure that everyone's on the same page with me. So groundwater is really hard to observe and understand. We can't see it the way that we can see our surface waters, like our creeks and our rivers. And so much of how groundwater behaves and where we find it depends on the hydrogeology of an area. It's really what's happening underground. And there's kind of two important things to think about when we think about hydrogeology. Depth to bedrock is one of the biggest things. That's kind of when you've hit the rock, it's the bottom of the aquifer, we're not going much further. With the caveat of, unless you're in the Colorado Plateau, that's a different conversation. We're not having that conversation here today. And also depth to groundwater, which is very influenced, again, by the hydrogeology of an area. So this cross-section I have here, also I love to dig into the old reports to find things because they often have a much nicer kind of conceptual diagram of how things work versus our more modern diagrams that can you get lost in the sauce sometimes. So this is a cross-section from a little west of Bowie to a little east of San Simon. So we're looking at kind of along this purple line. This point right here corresponds to that A, and then that orange point corresponds to that, what we call A prime, with the orange circle. So that's kind of the transect we're looking at across this basin. So what you see is at first, this depth to bedrock. So this area really changes across the basin depending on where you are. In general, it's much shallower when you get closer to the mountains that kind of bound the east-west boundaries of this basin. And then it gets much deeper throughout the center, especially towards the San Simon area. It's kind of like a trough that runs across the basin. Another important thing to know about this area is that there's this blue clay unit. It's this confining unit. And so this starts to get into the different types of aquifer and well conditions that you'll find depending on where your well is located. So up closer to the mountains, you tend to have this more unconfined area. Below this blue clay unit is where you find those artesian well conditions, or those old flowing wells. So this water below the clay is basically under pressure. So when you put in a well, you're kind of sticking a straw in it so it can pop back out. That's a little bit different than what you find in the unconfined, kind of this upper water table area, which is not a pressurized aquifer, but it does have a lot more connectivity to the ground surface. And so we can also map this out and translate, these cross sections, which just kind of run across an area, to also thinking about how does this depth to bedrock look in plan view. If we're looking at a map, we can plot them in terms of contours. And again, what you see, so these lighter, the yellows and the oranges, that's much more shallow depth to bedrock. And then these darker colors that you see in the center, that's a much deeper depth to bedrock. So if you just kind of imagine like a bowl that extends, and that is how a lot of the aquifers in the basin and range look across the southern and kind of northwestern part of the state. This is very typical geology, but it's really helpful to understand. And so we've talked a little bit, I mentioned a little bit about kind of pre-development conditions. In that same report, I love when these reports kind of do the work for you, but they have this really nice conceptual model of how things looked before and then after development. So one thing that I really want to call your eyes to is we're looking at the mountains, and then kind of that cross section we just saw. We kind of have this little unconfined area, and then you have the clay unit, and you have a couple different stories happening. So in this area, you tend to find your recharge really concentrated at the mountain fronts and happening through your ephemeral streams or your streams that only flow in response to rainfall. What you also see is that in your upper water table, as it flows out, that there used to be this connectivity where you used to have groundwater coming out in the Cienega at the headwaters of the San Simon River and supporting shallow groundwater here, and also riparian vegetation. So some of that groundwater would go back into the atmosphere as evapotranspiration. You have a little bit of a different story in this lower unit. It comes into these confined conditions, and it continues its flow kind of northward and westwards towards the Gila subbasin. Now, what happens when you have development is we start to stick in some wells. We stick in some wells in the upper aquifer, we stick wells into the lower aquifer, we pump out that water. As we're pumping out that water, we're lowering water tables to beyond where the Cienega can access them in the San Simon River. What also happens is as you're pumping out water and you're using it for agriculture, you can also get, trying to think of a less technical word here, but you can get incidental recharge, sometimes return recharge from these agricultural areas back into the upper aquifer. The recharge that we get from agricultural practices has, in general, decreased over time as our agricultural practices become more efficient. So the more that we develop water efficient irrigation practices, the more that we're maximizing every drop for the use by those plants. And as we do that, we kind of lose that return flow that would be going back into the aquifer. And I'm here to deliver some bad news. The number that everybody wants to know, how much groundwater do we have in our savings account, is not available. There are estimates that we can develop, But this is actually a number that, in many ways, if you're talking to earth scientists, can feel very ephemeral. It's a fundamentally unknowable number in the way that counting the grains of sand on the beach is a fundamentally unknowable number. We can develop estimates, but so much changes based on all the fine-scale happenings of the ground beneath our feet. The other thing to distinguish is you might have that water in storage, but if it is many thousands of feet deep, you're not going to be able to access it with current pumping technologies. It might be of a much more impaired water quality that's not fit for use. So the groundwater in storage is also not the groundwater that is necessarily accessible to people who are looking to really use it and put it to use for our lives, for our economies, for our environments. But that doesn't mean we don't know anything. It's just that I like to get this out of the way off the bat. And again, there are estimates that do get developed. There are assumptions that you can make to kind of bound in these numbers. ADWR does release estimates of groundwater in storage through their supply and demand reports. And I did see that the supply and demand report for this basin is due to be released in December of this year. They typically get released the first week of December, so that will have a lot of additional information for you guys for your basin. We can also use a lot of different types of science to understand, in general, our incomes and our expenses. So even without knowing your account number, you can get an idea of how your account is changing with a few other clues. So one of the things, and this is another thing I like to get off from the bat, is when you have large changes in groundwater storage, when you have large decreases, especially in your account, you get what we call land subsidence. And land subsidence is essentially, think of that flooded sandbox that I talked about earlier and start pumping water out of that sandbox. So that water is kind of holding those pores open. But as you pump out that water, that sand starts to then collapse on itself. And then you start to get some changes in the surface. That is essentially what land subsidence is. We tend to see these a lot in our alluvial aquifers in our basin and range. So this is kind of the map across Arizona. And this is about where our basin and range province ends. And then we get into our transition zone with the Mogollon Rim. Then we're up on the Colorado Plateau. So when I'm talking about the basin and range, it's basically this area here. We see this all across this area because, again, we have that bowl-based geology that's happening. And this is also where our most productive agricultural regions are in our state as well. This is, we can also measure this from space using satellite data. ADWR also tracks this information. This is the changes in land subsidence from May 2010 to April 2025. This is about 15 years of change overall. We tend to see it concentrated in our major agricultural regions. It increases with increasing drawdown. So this is a major clue that we can use to understand how is our account changing. On the other hand, I'm not here to just deliver bad news. I'm sorry, you guys have had a rough morning. There is also groundwater recharge in this region. And in this region especially, compared to the areas in the Basin and Range province, you guys have your groundwater recharge, as I mentioned before, really focused in the mountain fronts and through your stream beds. You guys also do have water coming in from adjacent basins, going out from adjacent basins. It's really that runoff and that infiltration of that snowmelt and the rainfall along the mountains that brings so much of that water back in. You do also, as I mentioned, get some recharge from agriculture, but those numbers are becoming less and less over time as we get more efficient. And one thing that we like to use are groundwater levels. There is no single better data source than groundwater levels from actual wells. Everything else is some measure of guessing and assumptions, some degree of change. We can measure a lot of things from space as well. But the holy grail of data is groundwater levels. And one of the most unpopular things I will say is that having communities support reporting of groundwater levels is incredibly important and incredibly valuable to help us understand what is happening across the state, what's happening in individual basins. Better data means better modeling, which means better decision support, better understanding by communities. And so what I'm going to focus on is kind of this area, again, centered around the Bowie and San Simon area. That's kind of where you have the most dynamic kind of activity in your groundwater happening. It's where you have a lot of the agriculture centered in this region. And so I'll dig into that on the next slide. Another thing that we can do is look at changes over time. So this, it's probably a small figure for a lot of you in the back, but there are changes in your water level, and most of the dots are red, that there's some kind of negative decrease. But there are also, and I guarantee you cannot see this from the back, but there are also blue dots. So groundwater levels can go down, they can also come back up. So here's some groundwater levels that I pulled from the groundwater site inventory database. This is managed by ADWR, and it's one of our best sources of data. The actual wells I chose based on a previous ADWR report, so I knew which wells were coming from which aquifer, but I pulled more current data from them. So what we have here is hydrographs over time from our lower aquifer. So this corresponds to this purple dot. I tried to color code it to make it easy for you guys and for me as I'm talking. So what we see is kind of this overall consistent decrease in the lower aquifer over time. These are like data that they say don't count, ignore this, there's pumping happening. So we're gonna ignore the red dots. We're just gonna focus on the green circles. So in the lower aquifer, you see a pretty consistent decrease over time. And in the upper aquifer, it's a little bit of a different story. And so what you see is, in some cases, I mean, in general, a pretty consistent decrease over the long run. But again, what I want you to pay attention to is down here, there is a big increase that happened in a very short period of time. And this is that early 1980s when I said we switched pumping. And then again, you see it up here. You have an increase that happened pretty dang fast. This is from 100 to 200 feet below ground surface. So that's not a small jump. This is only 20 to 60, so this is a smaller axis. So in the upper aquifer, you can see some rebound as that pumping got reduced. This is good news. You do not see this in many basins across the state. You guys really have a responsive aquifer to what you guys are doing on the surface. The lower aquifer is a little less responsive. But there are things that we can do to increase groundwater levels and increase recharge across the state. In fact, this is something that Arizona is really good at. A lot of our recharge across the state has really been driven by imports by Colorado River through the Central Arizona Project. This is an example of the CAVSART facility outside of Tucson, where we have big infiltration basins to recharge groundwater. You guys are probably like, why are you telling me this? We don't have Colorado River here. There are also things that people are doing in other parts of the state that don't receive Colorado River water, such as this work being done in the San Pedro, also in Cochise County, where we see groundwater levels coming back up, and they are not using Colorado River water. They're using urban enhanced runoff. They're helping link flood control efforts with groundwater recharge efforts. They're thinking about how to creatively use other sources too, like treated effluent. The most important thing here is collaboration and partnerships, sharing learning, sharing resources, and communities have a really active role to play in this. And the Arizona Cross Watershed Network is also creating a groundwater working group to really support communities in this. So I'm going to give a quick recap, and then I'll also give a quick little plug if you guys are interested in talking about this further in your community. The first, you heard me say this many times, you guys are not too different from the other aquifers and what's happening in the Basin and Range province. There is a lot of knowledge and experience to be shared across the state here, and a lot of experiments. But you guys are getting a little bit more recharge than what I'm seeing in some other places. Your recharge is in your mountain fronts, it's in your stream channels, it's coming from snow, it's coming from runoff, and you're also getting some in your agricultural fields. And you guys can really help shape the future and shape understanding across your community. We have a project called the Rural Groundwater Resilience Workshops I'm involved with in partnership with ASU. And if you guys want to have a deeper conversation, think about what your community can do to help support your economy, support your environment, discuss your concerns, we're very happy to talk with you further about that. And I think that was it. Thank you.